let's, again, what we're doing now, continuing what we did in the last clip, we see that there are certain types of solutions that come out of this equation for a mechanical oscillator with linear drag force. We've seen that there are various solutions that can come out of this depending on whether gamma is 0 or not and the relative size of gamma, k, and m. So let's look at an example of a solution of this nature. Let's say our solution is x of t equals, let's say, 2e to the negative 2t plus 8e to the negative 3t. What's that solution going to look like? First of all, let's just think about the function 2e to the negative 2t. If we were to graph that function, its value would start at x equals 2, graph of x versus t, and every time 2t increases by 1, it should be clear that the value of the function is going to decrease by a factor that's equal to e, because of course if 2t changes by 1, then e to the negative 2t is going to change by e to the negative 1, which is the reciprocal of e. Now e to the negative 1 is about, I think, 0.37, a little less than 0.4, so that when 2t changes by 1 unit, this function is going to decrease to a value about 40%, a little less than 40% of its previous. So let's just say that our unit is this. So here's a unit of 1 on our t-axis. If 2t changes by 1, that means t is going to change by 1/2. So that between here and here, this function is going to decrease to about 40% of its original value. Okay, so this y value here is about 40% of this y value. If we change by another 1/2, 2t changes by another 1, and we're going to decrease to 40% of this, which is going to put us down here. So our exponential function is going to probably look something like this, and it's going to approach the t-axis. And beyond this point is going to be very close to the t-axis. We see how we approach the t-axis as an asymptote. So this would be our graph of 2e to the negative 2t. What about a graph of 8e to the negative 3t? Well, 8 is way up here, and when t equals 0, of course, this function is equal to 8. But this function will decrease to about 37% when 3t changes by 1. And that occurs when t changes by 1/3. So we're not, well, I guess we could write the 1/3 and 2/3. And those aren't written very clearly. But the 1/3 and 2/3 points on the interval from 0 to 1. So if we start here at 8, we're going to increase down to about 37% by the time t gets to 1/3. So 37% of that is, well, probably about 3. So from here we're going to increase from here all the way down to here. Then if we change t by another 1/3, this is going to decrease by another, or to another 37%. Probably to a value around 1. And if we go another 1/3, we're going to be down to 40% of this value, which is probably not much bigger than the value of the e to the negative 2t function. So we see that this function decreases pretty rapidly, and it's not going to be too much longer before this graph, decreasing more rapidly than this one, crosses the graph. So that despite starting at a much higher value, this function decreases more rapidly and will eventually be less than this function. So if this is our function 8e to the negative 3t, the graphs are going to cross maybe about here. Then this function is going to become insignificant. The 8e to the negative 3t is going to become insignificant compared to the 2e to the negative 2t. And even more to the point, beyond this value, wherever the graphs happen to cross, both functions are going to be very small. We're going to be approaching the t-axis. We're already going to be very close to the t-axis, which is going to be an asymptote for this function. So here we see, in dotted lines, we see these two functions. If they're added, well, at t equals 0, we're adding values 2 and 8, we get 10. At any other point, whatever we add from this function is going to give us something a little higher than this function. We see that the sum of the two functions is going to behave something like this. So here's our x of t equal 2e to the negative 2t plus 8e to the negative 3t. Now, of course, we can do some algebra and some calculus and so forth and analyze this function a little more thoroughly, but we want to get the idea of how these solutions combine to give us a solution of our graph. Now, this graph would correspond to an oscillator that's released 10 units from the equilibrium position. So if equilibrium is here, the oscillator is released from here 10 units away, and it approaches at first rapidly and then more and more slowly to the equilibrium position.